8.2, we're going to continue the statistical test. So we're still going to have step 1, step 2, step 3, step 4, step 5. Many of the steps are exactly the same, and so I'm going to point out the ones that are the same, and then I'm going to point out some of the differences. Now, one of the biggest differences is sigma is unknown, so now we're going to use the student's t-distribution instead of the z-table. So if you'll notice step 1, the null and the alternate exactly the same. Mu is equal to some number, alternate is mu is less than, greater than, or not equal to some number. Now, where the first difference is in step 2. Since sigma is unknown, we calculate t because we have s not sigma, and so we have x bar minus mu divided by s divided by the square root of n. So we will not use the z table, we will use the student's t distribution. And here in a little bit I'm going to show you how to use that student's t distribution. So step 3 is where the big change is because we go to the t-table to find the p-value, and it is different than the z. Step 4 and step 5, exactly the same as the last section. Step 4 is comparing the p-value to alpha. If it's less than or equal, you reject. If it's greater than, you fail to reject. If you reject, there's sufficient evidence, and if you fail to reject, there is insufficient evidence. 4 and 5 will remain consistent through all of Chapter 8. So now what we're going to do before we actually do some examples is we're going to look at how the student's t-distribution works. So I want you to get the student's t-table out. Now, if you recall, and hopefully this one you can see a little bit better, we used this before when we did DF, degrees of freedom and confidence. So we're not going to be using that row right there. What we're going to use is the one-tail area and the two-tail area. Now, the alternate hypothesis will be less than or greater. So if it's less than or greater, then you have a one-tail area. Or the third option is not equal to, and that is your two-tail area. So here, these top 2 rows in green on my sheet is where you will find your p-value. Now, what we will be doing is looking for the t that we calculate in step 2, the test statistic. We're going to be looking for that number in here. So let's just do some examples of how to use the t-table before we actually do an application type problem. Now, this whole sheet of our notes is just learning how to use the t-table. One thing I want you to look at is in every one of these I have put n equals 12. So I went ahead and said the DF is 12 minus 1 or 11, okay? Now, the confidence interval is what we're not going to have to look for. Okay, so left-tailed test means we have a one-tail area. N is 12, so my DF is 11, and T was calculated. So step 2 is the calculation of the test statistic, so that's already been done for us. So the T that was calculated was 2.201. So what we're going to do is we're going to go to the table. Our DF is 11, which is right here, and I'm looking for 2.201. 2.201, which is right here. Now, we were told it was a left-tailed test, so that means it's a one-tail area. So I'm going to travel up, and the very top row was the one-tail area. So this value where my finger is what your p-value is, which is 0.025. So my p-value is equal to 0.025. Now, one thing that we're going to find is that the majority of time when we use the student's t-distribution table, our p-value is going to most of the time be located between two numbers. So I'm going to show you that example here. Now, for my online students, when you use WebAssign, it doesn't give you the option for between. Don't worry about it. Just answer the question. I have given those as 0 point value on that. they actually go into the calculator and find the exact p-value, which I do not have you do. But again, you will not be counted off for that, so don't worry about that. So when you take the test on Blackboard, you will be given the option to put them in between, and that's what I'm most interested in. All right, so N is 12, so my DF is still 11. We have a right-tailed test, so that means we have a one-tail area, and T is equal to 1.327. So again, I'm going to go to 11, and I'm looking for 1.327. So as I look, I have 0.697, 1.214, 1.363. Well, 1.327 is in between these two values. So it would fall right here in between these two values. So what I'm going to do is travel up to the one-tail area, and my p-value will be in between these two numbers. So my p-value is in between 0.125 and 0.100. Now, when you actually write that, you need to be careful because 0.100 is the smaller number, so it actually needs to go on the left. So my p-value, I don't know its exact value, I just know it's in between these two numbers, and that will be sufficient in order to do our tests. Okay, now look at this one. We still have the same DF, but now I have a two-tailed test, so I need to use the two-tail area. So when I travel up, I want to use here where it says two-tail area, so be careful there. So 2.56. So on 11, I'm looking for 2.56. So there's 2.201, 2.718. So 2.56 falls in between these numbers. So I'm going to travel up and I'm going to stop at the middle green row because that's the two-tail area, and it tells me my p-value is between 0.05 and 0.02. And again, 0.02 is smaller, so I put it on the left. So your p-value would be written as such. All right, next example. Left-tailed test, so we're going to go back to one-tail area. DF is still 11, but notice the T is negative 0.997. When I go to my table, I don't see any negative numbers in here. Well, we have to recall that all of this is symmetrical. So since it's symmetrical, I can look at this as its opposite, or 0.997, and that will be sufficient. So if you calculate a negative test statistic, your test statistic is negative, but when you go to the table, you're looking for its opposite, or 0.997. So again, here is 11. I'm looking for 0.997. Well, that falls in between the first two, and I'm looking at the one-tail area, so it's in between 0.250 and 0.125, and 0.125 is smaller, so I put it on the left, and then I put the larger one, 0.250, on the right. Now, there's two more scenarios that could occur when you're dealing with the T table, so I want to be sure that we look at that. All right, two-tailed test, so we're looking at the two-tail area. DF is still 11. Now, my p-value, or I'm sorry, not my p-value, my T calculation, my test statistic is 0.234. So here's 11, and I'm looking for 0.234. Well, the smallest number is 0.697, so 0.234 falls to the left of that. So I am traveling up to the two-tail area, which is in the middle, and I have 0.5, and that would tell me that my p-value is to the left of that number. So I look at this row of numbers, and as you go to the left, the numbers continue to get larger. So we have 0.5. If we went further to the left, those would continue to get larger. So our p-value is larger or greater than 0.5 or 0.500. And then the last one, right-tailed test, that's a one-tail area. Our DF is still 11. Now I'm looking for 6.103. So here's 11, and I'm looking for 6.103. Well, if you'll notice, the largest number is 4.437. So 6.103 would lie to the right of that. So I travel up to the one-tail area, and I know my p-value would fall to the right of 0.0005. So as I read this row of numbers, the numbers continue to get smaller. So the further you would go to the right, it would be smaller or less than 0.0005. So that does not occur very often, but it can happen. So be prepared for that. All right, now what we're going to do is we're going to actually do a couple of the statistical tests. We're going to go through all 5 steps. So if you'll turn to page 437. Let me get my book turned to those pages. 437, number 12. It's at the bottom of the page. Let X be a random variable that represents the pH of arterial plasma. For healthy adults, mu is equal to 7.4, so I already wrote that here. A new drug for arthritis has been developed. However, it is thought that this drug may change the blood pH. A random sample of 31, so N equals 31, patients with arthritis took the drugs for 3 months. Blood tests showed that the sample mean, X bar, is equal to 8.1, and the sample standard deviation, S, is 1.9. Okay, that's important because sigma is unknown, so this tells me right here we will calculate a t-value, not a z-value, which means we use the student's t-distribution. But before we get there, we need to read the last sentence to set up our null and our alternate. Use a 5% level of significance to test the claim that the drug has changed either way the mean pH level of the blood. So, mu is equal to the 7.4. The alternate, it said, has changed either way. That would be is not equal to 7.4. Now, we don't draw a normal distribution or a bell curve here because with the student's t-distribution, this alternate, since it is not equal to, tells me I will use 2-tail area on the student's t-distribution. Okay, so I don't have to draw the picture because all I need to know is it's a 2-tail area. So here, because we have S, we know we use the student's t-distribution, which means I'm going to calculate a t-value. So I'm going to plug in my numbers to my formula, which it's X bar, 8.1 minus mu, 7.4, divided by S, 1.9, divided by the square root of 31. Don't forget where your parentheses go. And when you plug that into your calculator, and you can round to 2 decimal places. If you go further than that, that's fine. You get 2.05. So now in step 3 is where we find our p-value. And this is the number we're going to look for in the student's t-distribution. And then, of course, the other thing we need is the DF, which the sample was 31. So we do 31 minus 1. So the DF is equal to 30. So I'm going to pull up my student's t-distribution and I'm going to find 30. Now, remember this is a 2-tail area, so we're going to use the middle row at the top. And I'm looking for 2.05. Well, as I travel across, here's 2.04. We have 2.05, which is larger than that, but yet it's smaller than 2.457. So it's going to fall in between these numbers. So I'm going to travel up in between these and go here where we have our two-tail area, and my p-value then will be between 0.05 and 0.02. So my p-value is between 0.02 and 0.05. So now in step 4, I'm going to compare the p-value. Now it's a little bit more difficult to compare the p-value because we have a range instead of an exact number. So I've shown a number line because I'm going to show you how this works. Our p-value is somewhere between 0.02 and 0.05. So here's 0.05, here's 0.02, so my p-value is somewhere in between there. I don't know the exact, but I don't have to know the exact. Then I go to the problem. So number 12 reads, use a 5% level of significance. So alpha is 5%, which is 0.05. So 0.05 is right here. Here is my alpha. Well, all of this that is shaded, although it's very close to alpha, it is slightly less than. So since it is less than, we know that we will reject, because less than means to reject, the null. So when we reject, we know that we have sufficient evidence at the 5% level of significance to conclude the drug changes the average pH level in blood to be different than, because I used my alternate and it was an is not equal to, so different than 7.4. So there is a problem that uses all 5 steps, and this time using the student's t-distribution. So we're going to look at one more, so hopefully you can get a better idea of how to do this. Now we're doing number 16. That's on page 438. It says, unfortunately, arsenic occurs naturally in some groundwater. A mean arsenic level of 8, it says 8.0, that's the same thing as 8, parts per billion is considered safe. A well in Texas is used to water cotton crops. This well is tested on a regular basis. A random sample of 37, so n equals 37, tests gave a sample mean X bar of 7.2 parts per billion arsenic with S, and again it's important to recognize this is S because you're going to use the student's t-distribution. So my alternate and my null, well, we already know mu is equal to 8. So this will be mu is equal to 8. And then it reads, does this information indicate that the mean level of arsenic in this well is less than? So mu is less than 8. Now, I'm not going to draw a bell curve because since I have S, this alternate of less than tells me to use one tail area. That's all I need to know in order to use the student's t-distribution. So now what I'm going to do is calculate that test statistic, and we know it's a t-value because sigma is unknown. So we have 7.2 minus 8 divided by 1.9 divided by the square root of 37. My parentheses, and then I go to my calculator and do that calculation, and you should get negative 2.56. So now I know I'm going to use the one tail area. I'm going to use the student's t-distribution, and I'm looking for negative 2.56. Well, remember there are no negatives on the table. So for step 3, although I calculated a negative number, I'm going to leave that a negative number. But when I go to the table, I'm going to look for t is 2.56 because it is symmetrical. I also need my df, which is n minus 1. N is 37, so 37 minus 1 is 36. So these are the values that I am looking for on my table. So Find 36. There is not a 36. Okay, there's a 35 and a 40. So I'm going to look at the bottom. For degrees of freedom not in the table, use the closest DF that is smaller. Well, the closest DF that is smaller is 35. So we're going to use 35. And I am looking for 2.56. Oh, let me move that up. 2.56. There's 2.4 and 2.7. So it falls in between. 2.56 falls in between these. So I'm going to travel up, and we are doing a one-tail area, so that's at the very top, and I find 0.01 and 0.005. So it is between 0.005 and 0.01. So now what I'm going to do is compare that to alpha. So we have 0.005, 0.01. So here's 0.05, here's 0.01. So my p-value is any number in between here. And I'm going to compare that to alpha. And for this particular problem, it says to use alpha of 1% or 0.01, which is right here. Now again, it's very close, but it is slightly less than. So since it's less than, we will reject the null. And if you reject the null, that means you have, let me move this up so I can get the whole thing in there, that you have sufficient evidence at the 1% level of significance to conclude the average arsenic level is, and then go back to your alternate, and the alternate says that it is less than 8 parts per billion, period. Sufficient. It's sufficient enough evidence to prove it's changed, and it is now less than 8 parts per billion. That is 8.2.